Greetings. Welcome to Lecture 4. We will discuss Coulomb's law and electric fields. This lecture is a recorded lecture. I'm currently in Washington, D.C., unfortunately. Let's start with let me use my iPad here. Let's start with some news or some announcement. We have uh, decided the office hours for all TA and LAs of this class and the instructor, which is me. Okay. And we encourage you to go to the office hours. The office hours are listed on Canvas. So if you go to Canvas, let's see if I can do it right now. Canvas. It will be on the first page. And if there is any changes, we will upload a new list. Some of the office hours are in person, such as myself. Some of them are hybrid, like cross office hours. And the other, I think most LAs. So Jihad and Andy will do their office hours on Zoom, and Pranav will have an in-person office hours. Okay. So let's recap. Sorry, this is not right. So let's recap. So from lecture 3, we know that everything is made of atom, and every atom has a nucleus. In a nucleus, there are protons and neutrons, and surround the nucleus, there are electrons. And we also talk about uh, some properties such as masses and also electrical charges. The electrical charge of a single electron is minus E, a single proton is plus E, and neutron has a neutral charge. I hope that thing, you still remember that, right? It's from your high school. And then we started learning about this value here, which is a vector force. Force is a vector. The magnitude, you can put magnitude, is basically this one, K times charge 1 times charge 2 divided by the separation, all of these R's. And then we ended the lecture with a discussion about this R hat, or a unit vector. So a unit vector basically, and I think I mentioned that this one is almost, so basically same like one and then a direction. Okay. So unit vector, so let me explain it more explicitly. So unit vector is the vector that connect the center of masses of the two charges. Okay. And it tells us the direction. Okay. Let's say from 1 to 2, then it goes like this. That's the direction. But the magnitude of the vector, again, every vector has a direction and a magnitude. The magnitude of the hats or the unit vectors is always 1. This is the same like when you go to Fry's and you buy a dozen of egg, or like 2 dozens of egg. You don't say you buy 2 times 1 dozen, right? 1 is implicit. So in unit vector, the magnitude is always 1. It is profound because it gives the direction. Without the unit vector, then all you have is only a magnitude. Okay. So let's look at these 3 examples. Let's say we have positive charges here, 2 positive charges. We know that if the charges are alike, they have the same signs, then we get repulsion between 2 charges. Okay. If the charges are different, then we have repulsion. And the direction is along the vector that connect the center of masses. For one particle, it points away from the other particle. This particle also, it points away from the other particle. Okay. So in these three examples, let's say if we double the force or the charge of one of the charges, then the force becomes a factor of 2, right? So this one is twice longer than the force on the first row. And in this example, if we increase the separation by a factor of 2, then the force will be a factor of 1/4, because K times Q1, Q2 divided by R square, right? If we increase R by a factor of 2, then the value will be smaller by a factor of 1 divided by 2 square. Okay, I hope this is clear. Next, so we discuss about unit vector, and we will do this simulation when we discuss about electric fields. Uh, most of you, so next is an example, but we will do it kind of fast because all of you have read this on perusal. So this is an example of hydrogen atom, and we briefly touched hydrogen atom in the beginning of the class when we compare the value between gravitational force and electromagnetic or electric repulsion in a hydrogen atom. Right? All the numbers are on perusal. So for example, the Bohr radius is given here. This is the radius of a hydrogen. And so if we want to calculate the electric field, the electric attraction between protons and an electron, if we know the distance and we know the charge of a single proton and a single electron, then we can calculate the value. I'm just putting all the numbers here. If you want to calculate the mass of the electron, then you can look the number up. Let's say on Wikipedia, the mass of electron is given here, which is 9.11 times 10 to the minus 31st kilogram. Mass of the proton is also listed there. If you put all the numbers, and and I will ask you to do to check the calculation here, then you can calculate the magnitude of the gravitational attraction between an electron and a proton. And you can also calculate the attraction between an electron and a proton, right? You can use the numbers here, and K is given here. And if you then compare the value, and we did this in the, I think, second lecture, the ratio is basically the number that people often use is 10 to the 40th. But if you want to be accurate, is about 10 to the 39. And if you're curious whether there is a name for that, that's equal to approximately 1 duodecillion. So it's basically 1,000 billion, 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 billion. So we know that the electrostatic interaction is far stronger than the gravitational interaction. The reason why we don't feel electrostatic repulsion as much or attraction as much, because most atoms in the world is neutral. Okay? So all of this is recap. This is the reason why I'm going really fast. All right, so this is an iClicker question. So I'm going to ask you to pause the video after you first read this question. Okay? Can you do that for me or for yourself? Okay. So there are two neutral marbles, and we separate these two marbles, and they are identical. They have the same dimensions. They are separated by 10 centimeter. Okay, 10 centimeter. Uh, 10 centimeter. Okay. If you want if you're not sure, 10 centimeter is basically 0.1 meter. Okay. Estimate the force between the marbles if 100 billions electron, 100 billion with B were taken from one and transferred to the other. Okay. So this is actually a really good problem. Okay, first, you should try doing this problem and pause the video. Um, all right, welcome back. So initially you may think that, especially because the title of the slide is neutral marbles, that there is no electrostatic interactions between these two marbles. But one thing that you should uh, be aware of, if you take electron from one object, then the object will be positively charged. Okay. And if you put electron to a different object, then that different object will be negatively charged. Okay. So this is the answer. So basically Q1, let's say Q2. Again, Q1 and Q2 is up to you, meaning you can either assign the one on the left as Q2 and the one on the right as Q1, or the opposite. So Q1 is positive because we take electrons away, and Q2 is negative, right? Because 10 to the 11th, because we put the electron from one marble to the other one. And then all you need to do next is F is equal to K times Q1 times Q2. And then this is just the magnitude divided by R square. So K, which is 9 times 10 to the 9th. Q1 is 10 to the 11th E times minus 10 to the 11th E. So there will be attraction. And right now we only care about the absolute value. And then this one is 0.1 meter square. Okay. So the value is basically 10 to the 22nd divided by K times E square. And then this one is 10 to the 20th K times E K times E square. Okay. So I did all calculation for you. K is 9 times 10 to the 9th. And then E is 1.6 times 10 to the minus 19th. And when you put all the numbers, the answer that you get is 2 times 10 to the minus 4th Newton. Okay. If you're not sure, if you didn't get it right, that's okay. But the next time you see a similar problem, you should be able to solve it. All right, good. So next, what I want to discuss is what happens if we have more than two charges. Okay. So far, we only discuss, let's say, two charges, Q1 and Q2. So what happens if we put in the one that I just highlighted is Q1 and Q3. But uh, what happen if I also add Q2, right? The blue one. We actually covered this in last lecture, but one of your friends asked me the question, and that made me realize that I didn't explain it. Uh, I was rushing it because I only had like few minutes to explain that slide. So what I want you to do on Friday, if you're not sure, you should stop me in class, not after class, okay? Because this is probably the, I don't know, 732nd time that I'm doing this problem. All right, so basically, what is the principle of superposition? Principle of superposition, basically, we can approximate the solution only by adding the vectors from all from all interaction pair or pair interactions. So if we want to calculate the force that Q3 experience, then what we can do first is we can calculate the force, repulsion force, in this case between Q1 and Q3, okay? So we can calculate that using Coulomb's law, right? Which is K Q1 Q3 divided by R1 3. So this is R1 3, right? Let me move this thing here. And then let me change color to blue. Blue. Okay. And then F23 is equal to K Q2 Q3 divided by R23. And R23 is here. So those are the magnitude. In terms of the interaction, we know that F13 will be along this direction, the direction that connects the center of masses of Q1 and Q3. So that's one. Second, we know that it should be a repulsive force. Okay, so instead of pointing this direction, which is not right, it should point this direction. Okay. Similarly, the force, the repulsion force between Q2 and Q3 will be along the direction that connect the center of masses of Q3 and Q2. But instead of a repulsive force, it will be an attractive force, right? Because it's positive and negative. So it will point, instead of pointing this direction, which is not right, it points toward the other charge. So you have two forces on Q3, and the sum is the sum of these two vectors. You should know how to do vector addition, which is like this. Okay, that's the, I don't know, some books use FR, basically resultant force. Clear? For as I remember, there is a homework, a one homework problem that involve vector addition. Okay, so next I want to talk about a new concept, which is the theory of fields. Okay, the theory of field, we will cover that over the next few lectures, and also when we talk about magnets. Okay, uh, so many of you are pre-meds. So there is this quote by Albert Einstein. So basically, Albert Einstein, of course, he is smart and he knows the importance of, for example, Darwinian evolution. But for him, the most important theory is actually the concept of field, something that we will discuss in today's lecture. Okay. Uh, and instead of spending the whole lecture about the history of the field, it's basically something that is significant. Faraday was often gets credit on the development of the field theory. Different people may have different, if you ask different people, they may have different opinion. But another thing that people were confused in the old days. Well, in the old days, let me take it back. So in the old days, people struggle with explaining the universe. So initially, people have different types of energy. So instead of potential energy, kinetic energy, in the old days, everything has energy. Let's say the energy of this drawer, right? And then the energy of this cable, this USB-C cable, the energy of this Apple Pencil. Uh, but physicists and chemists and scientists came up with different construct uh, that clump uh, energy into different classes of energies. Okay. So another thing that people get confused or not confused, puzzle or uncomfortable with is that energy or interaction can affect in the absence of medium. So there is this nice quote by Isaac Newton. You can pause this video and read it yourself. So basically, if you want to learn about the history of science, we can, I can order pizza and we can sit and discuss history of science. But it has a really interesting theory and interesting history, and we can spend more time if you are interested in the history of science. But if you ask me, what do you need to do to solve the homework problem? Uh, we can, I think I can help you with that also. So the topic that I want to talk about right now is electric field. Okay, so electric field is defined. So this is a definition as the Coulomb interaction divided by attached charge. So many of you discuss what is attached charge in Perusal, which is very wonderful to see that you guys are so engaged in Perusal. So electric field, before, we talk about two charges, right? Positive and negative, or positive and positive. But right now, to discuss a field, uh, one charge is sufficient. Okay. So let's say a single charge can generate field. Okay. And it doesn't require medium. Okay. And the field is everywhere, you know. It's a mathematical construct. Okay. Around you, there are fields. I mean, you don't see lines with arrows, but lines and arrows are the construct or the concept that we use to understand nature, or in your case, to solve homework problem. Okay. So what is this? So a single a single charge is sufficient to generate a field or electric field. Okay, but there is nothing, meaning there is a field, but there is no force. If you study philosophy or I don't know Japanese Zen or I don't know New Age, if you read New Age books, it's like clapping with one hand. With one hand, you cannot clap, right? It requires two hands to make sound. So similarly with electric field, every charge generates field only if there is a test charge or another charge nearby. There is either attractive forces, an attractive force, or a repulsive force. Okay. So electric field, I hope that the concept of field is clear. Uh, maybe it's not a bad idea to do uh, simulation. So if you want, so the link of the simulation is on the lecture notes. Uh, you go to PHET, and then you go to physics and electricity, magnets and circuit, and you use charges and field. Uh, let me clear the whole thing. So we can put a charge, and a charge uh, can produce a field. And there is no forces. It's just, every charge generates a field. Okay. And only if there is another charge, there is force. So for example, the test charge is always the charge of the test charge of a test charge is always +1. So closer the the closer the charge, the higher the force. Okay, right? By a factor of 1 over r square, or square distance, 1 over square distance law. This is something that Newton is famous for, and don't get confused by Hooke's law. Hooke's law is not 1 over square distance. Hooke's law is 1/2 times kx squared, right? Uh, you can also place negative charge, and for negative charge, the arrow points to the charge. Okay, and then if we place test charge, depending on how far we place the test charge, the force that the test charge experience varies. And the length of the arrow corresponds to the strength of the force. Okay? Good. So that's the direction of the field. For positive charge, the direction points outward. For negative charge, it points inward. Okay. One thing that I want you to realize that I only draw and your books only draw on 2D, but actually the field is 3D. It has a spherical symmetry. Okay, so it's not just 2D, but it's 3D. Uh, so the next thing that I want to discuss is the graphical representation. So some of you are good with numbers, with deriving equations, and that's good. Some of you are good with uh, conceptual understanding, which is amazing. But some people are pictorial. Some people love pictures, right? If you go to, for example, maps, so and then you can, well, this is really boring, but so this is South Mountain, and you can, okay, so I apologize. I thought that Google Map will have a topographical map. So basically, some people prefer seeing picture, and that's why we come up with this representation. So first, for drawing electric fields, you need to come up with a number of lines that you're comfortable with. So in this case, I use mathematical a code to draw the fields, and I choose 8 fields that corresponds to plus Q. And you need to be constant with drawing the fields. So for example, if you have half Q, then instead of drawing 8 lines, you draw 4. If you want to represent the field that 10Q generates, then the number of lines should be 8 times 10. Okay, and that thing is important because these field lines represent one, the direction, second, also the intensity. Okay? So in terms of the intensity, what people come up with is they think that what they do is they connect a line that is perpendicular from the field. Let's say like this. And there is a name of this line, which is equipotential line, and we will discuss that. And basically, they connect the line that are equal distance and perpendicular from the line, from the local line. And based on this diagram, so first I apologize that the drawing is not perfect, but basically in a region where the density of line is higher, so this one is, I don't know, maybe the circumference of this line is 10, let's say, and this one is 30. In the inner circle, there are 8 per 10 length. Right? So the other one has 8 lines, but the circumference of the circle is longer. So that means at this position, the strength of the field is less. Okay. Okay. All right. So electric field. This is an interesting problem. Again, this is an iClicker problem. I know that we are not in the classroom, but I want you to pause and try to solve this problem yourself, okay? Uh, all right. So I remember I made a mistake on this problem last year and students were not happy. So let's see if I can do it right. A small object with a charge of magnitude Q creates an electric field. Good. At 0.1 meter to the north of charge, so charge north, the field has a value of 2 directed to south. That's right. At a point of 0.5 to the west of charge, the field has a value of and direction. Okay, so please pause the video. All right, welcome back. So the field is described as F divided by test charge. Okay, so this one is equal to K Q prime divided by R square divided by Q prime, and this one is cancel. So it's K Q divided by R square, right? So basically E, again, we're only talking about the magnitude here, is proportional to 1 over R square. So since the distance decreases by a factor of 2 from 1 meter to half meter, then the value of the field should increase by a factor of, should increase by a factor of 4. Okay. So if initially 1 over 1 meter, and then it becomes 1 over 1/2 meter square, and this is equal to 4x. Okay. So 2 times 4 is 8. Okay, this is correct. And then it says that the, initially 1 meter, so if this is Q, when the Q prime is here, the field point down, that means Q is negative, right? So when the second charge or the test charge is uh, to the west of the first charge, then the field will go to the right. Right means to the east. So the answer is C. Okay, good. This is a nicer representation than what I tried before. Basically, all the circles are the point, all points with the same distance. So this point, sorry, this point have the same distance to the charge. And since the number of line per total length is less, then the field along this line is weaker than compared to the field along this line. Okay, good. And there is another demonstration that you can play with. Uh, okay. This is just the same thing, but if one of them is plus, the other one is negative. So the one on the left is plus, and the one on the right is negative charge. Okay. The difference is again the direction of the arrows. Okay. All right. So the next few slides are the magnetic fields from more than one charges. Okay. One charge can generate, sorry, Dirac magnetic field, I meant electric fields. So one charge can generate electric field. Multiple charges can also generate electric fields. And the way to find the direction of the electric field is by superposition theorem, meaning you generate a field from one charge and another, and then you do field from the other charge and you sum the field. Okay, so let me give you an example. So let's say in this example, the one on the left is negative, the one on the right is positive. So let's make that negative, okay, and positive, okay. So again, this is only negative, and this is negative and positive. And as you can see, uh, the field, let's do it. Yeah, something like this, right? So this one looks similar enough to the one that is more refined. Here, the number of point that this program calculate is very sparse compared to this representation. So using superposition theorem, we can calculate the field line between two charges. Okay, and I hope you remember what this uh, system is. This is a dipole. So if you have minus and positive, then the field looks like this. And there are many dipoles in chemistry, in biochemistry, and biology. Okay. Uh, if you have, let's, if you have uh, two positive charges, then the field will look like the one described here. And you can, again, continue playing with this program. Let's say you have plus here, then it's hard it might be hard to convince yourself that they're the same, but they do. For example, this one point up, this one point down. This is because the resolution of the of the simulation is not good enough. Okay? Or perhaps what I should do is actually do like this. Maybe this one is easier to see if I separate the charges. Ah, I see. This one is nicer. So if we put test charge here, it doesn't experience any Coulombic force, but if I put here, it start experiencing Coulombic force, okay? But not when I put it in this line here, okay? And we can also, instead of having discrete charges, we can have electric field between two surfaces. And here is electric field between positive surface and negative surface. Anyone knows what the system is? This is a capacitor, okay? This is a capacitor. You can find it in your cell phone, in if you see old school radio. And also, if you think about it, let's say this is cell membranes, sorry, cell membranes, right? And the reason why we have, let's say, proton pump is to maintain different voltage, different potential, which we will discuss. So my point is, let's say I don't know, sodium concentration outside cells is higher than sodium concentration inside cells. There is actually a field, right? And many physicists, perhaps many biologists, model biophysics, membrane biophysics as a capacitor, as two plates with charges. But back to the example, uh, the field again goes from positive surface to negative surface, and the field in the middle is uniform. Okay. Okay. I think this is the second from last slide. Okay. So this one, let's say we have a uniform field. Okay. A projectile with a negative charge is fired in the x direction. Okay. In a region of space where there is a constant electric field. If the acceleration in the plus y direction, that means there is a field that point up, right? What is the direction? Okay, if its acceleration is in the plus y direction, okay, this is the acceleration, sorry. Okay, I have to admit I made a mistake. So, uh, because I wasn't reading the problem. So, lesson to all of us, if the professor made a mistake, you should correct me. I know you're not here. And then second, before you answer a problem, you should read it carefully, okay? So the acceleration point up, okay? That means there is a field along the same axis, right? Every time you see acceleration, that means there is a force. And force is for electrostatic is equal to F is equal to E times test charge. The direction of acceleration, it points up. So what is the direction of the field? So the answer either B or C, right? It has to be along Y direction. Okay, so next you need to be careful because the charge is negative, okay? Because the charge is negative, that means if the field points up, then the charge will get accelerated down, okay? Because this is not a simple test charge. Test charge, the sign is positive. This is negative, okay? Since the acceleration points up, that means the field should point down. So C, so the answer is C, okay? All right, so If this is not clear, then feel free to email me and ask me to go over these two examples, like the previous example and this example in class or in my office hours. One thing that probably you don't know, in the old days, this is what people used to make TVs. So basically, you have a charge and you can control the trajectory of the charge by tweaking the fields, and the charge will land to a pixel and make it glow. So that's how to make a simple TV. Another way to do that is by using magnetic field that we will discuss in a month or so. All right. So this is the end of lecture 4. Enjoy the warm and sunny Arizona. I'll see you on Friday.